This is jet fuel. It was made with agricultural waste, water, and renewable energy. I'm standing at one of the only plants on Earth that does this. I came here expecting a story about solar towers and mirrors, fuel made from concentrated sunlight. But that's not what I found. What I found is actually in many ways a bigger idea. And honestly, it changed how I think about sustainable technology. So what is sustainable fuel and does it make sense? Let's figure this out together. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by Narwal. If you follow clean energy, you've probably been hearing a pretty simple story. Electrify everything. And when it comes to cars, buses, trucks, batteries are winning. But there's one machine where batteries will probably never work. And it's not even close. Jet fuel packs about 12,000 watt hours per kilogram. The best lithium-ion battery today, around 300. That is a 40x gap. But the problem is worse than the gap. When a plane burns fuel, it gets lighter. A 777 burns 150 tons of kerosene flying London to Sydney. Batteries don't get lighter. You carry every kilogram the entire flight. And many airplanes rely on this lighter weight for takeoff and landing loads. And critical systems like landing gear really take advantage of the fact that planes land lighter. And if you run the numbers, a battery-powered 777 would need a pack weighing 9 times the entire aircraft, over 3,000 tons. And a plane that size is not getting off the ground. Now, while we might be able to get batteries from 300 to 600 or 800 watt hours per kilogram, we're not closing that 40 times gap. Hydrogen? Airbus pushed their hydrogen aircraft to the 2040s. Short-haul electric flight is real, but covers maybe 5% of emissions. The other 95% is medium and long haul, flights where nothing replaces liquid fuel. Aviation accounts for about 4% of global emissions, and it's growing every year. And the industry's own body says 65% of the solution has to come from changing the fuel. Not the engine, not the airframe, the fuel. So what fuel then? Here's something I didn't fully appreciate until I started researching this video. You can build jet fuel from scratch. Take CO2, strip out the carbon, take water, strip out the hydrogen, stitch them together into chains of 8 to 16 atoms long, and you got kerosene, the exact same molecule that comes out of the ground, built from air and water. The chemistry is called Fischer-Tropsch synthesis. It was invented in 1925, and the fuel it makes is chemically identical to fossil jet fuel. Same energy, density, and it has the same performance characteristics. Put it into any engine today, and it just works as a drop-in replacement. Actually, it's better than fossil fuels because synthetic fuels don't have sulfur or aromatics. As a result, they burn cleaner, which is not only beneficial to the engines to make them last longer, but it means less particulate emissions out the back. But when I started mapping out what it actually takes to make this fuel, I realized the challenge isn't the chemistry, it's the ingredients themselves. You need 5 things: extreme heat over 1,000 degrees, a source of carbon, a source of hydrogen, storage because chemical plants can't shut down every night, and the Fischer-Tropsch synthesis to stitch it all together. In a perfect world, you'd get the heat from the sun, pull the carbon from the air, split water for the hydrogen, and run the whole loop on solar power. Truly circular economies. A guilt-free circular system where we could all fly around the world comfortably knowing that we're not hurting the planet. The problem is, every one of those core ingredients is its own engineering mountain to climb. But before we get into that, I gotta tell you about another piece of tech that I'm absolutely blown away by, and that's my Narwal Flow 2, possibly the smartest robot vacuum I've ever used. Most robot mops use spinning pads or flat mop heads, and they handle light dust fine. But the moment they hit a real mess like dried ketchup or coffee or a clump of yogurt, the pad gets dirty and just smears the mess all across your floor. The Flow 2 is different. It has a rolling track mop, and instead of a flat pad dragging across the floor, it actively scrubs at high speed with continuously self-cleaning with heated fresh water from its own built-in water tank. It sprays 140°F water for stubborn stains and a scraping bar that strips debris off the track as it rolls. This is the best mopping robot I've seen. It's seriously like magic. Just look at the amazing job it did when my boy spilled some yogurt the other day. This would have been a smeared mess before. The Flow 2 has dual RGB security cameras, and an AI brain called Narwal that recognizes everything in my house and adapts on the fly. It doesn't just detect obstacles, it actually knows what they are. Near a wall, it cleans within 8 millimeters. It sees your dog and keeps a safe 40 millimeter buffer. Pair that with 31,000 pascals of turbo suction and a dual flow tangle-free brush, it handles everyday surfaces and every mess, wet or dry, automatically. And the design is beautiful. Both the Flow 2 and the dog will be a conversation starter in any room you put it in. And the premium quality is something you can feel everywhere. The all-in-one base station self-empties for up to 120 days. Just fill the tank and you can let it do its thing. So if you're ready to reclaim some of your time and keep a tidy house, check out the amazing Narwal Flow 2 using our links in the description. Huge thanks to Narwal and you. Now back to the show. Pulling CO2 from the air, it's 0.04% of the atmosphere. It's incredibly diluted, the carbon dioxide. The world's largest district air capture plant cost over $600 per ton of CO2. Splitting water with solar heat, best lab results are around 5% efficiency. Concentrated solar, massive mirror fields, desert sunshine, and enormous capital. If you need every piece of that to be perfect before you begin, we're talking about billions of dollars investment for hopefully some return. That's a tough pill to swallow. But here's what took me a while to understand. You don't need every piece to be perfect. You don't wait for carbon capture when there's methane from cow manure that's going up in the atmosphere right now. You don't insist on solar towers when there's cheap wind power that the grid can't handle at 2 a.m. and it has to be dumped into the ground already. Instead, you focus on the part that's actually hard to solve, and you let everything else be plug-in. So I went to Germany to meet with a company, Synthesizing. Their first plant, Dawn, that I came to visit, opened here in Jülich, Germany. From the outside, it looks like a small solar tower surrounded by mirrors. From the inside, it's a proper chemical plant running in 3 different shifts. I'll tell you, when we visited, it was in the middle of winter. The plant wasn't running in solar receiver mode. At this point, you're probably wondering why the heliostats are covered in snow, which probably isn't good for solar capture, and you would be correct. But that very fact is what led me to realize the most important part of this technology. So let me start with ingredient 1, heat. You need over 1,000 degrees to drive the chemistry. And yes, Synthesizing did build the solar receiver that can do that. That's what we're standing in here. But when their engineers walked me through the plant, the first thing he showed me wasn't the solar tower. It was this.
And this is the electric gas heater. This is a unique device which you cannot buy on the market. So this is a 300 kilowatt electric gas heater, which converts renewable electricity into high temperature heat at 1200 degrees Celsius.
A 300 kilowatt resistive heater, so specialized you can't just go out and buy one. That converts any renewable electricity from the grid, from whatever source, to 1200 degree steam. Instead of obsessing about clean energy as an input, they hope that clean energy is the input and start with the next step, because that way you can run this and produce syngas even in winter, even in Germany. And that reframed everything for me. Right now, wind farms and solar plants regularly produce more electricity than the grid can absorb. In Germany alone, terawatt hours of clean energy get curtailed every year, switched off and thrown away because there's no demand for it. So what if instead of doing that, we produced jet fuel? You don't need billion-dollar fields with mirrors to collect sunlight. You just use the energy that you already have. Then there's ingredients 2 and 3. Carbon and hydrogen. Both came from the same source, biogas. Methane from agricultural waste, manure, food scraps, stuff that leaks out from decomposition as greenhouse gases anyway. So not the perfect circular loop, but a real one, available now. And it's available everywhere on Earth. Like a lot of companies we've been covering recently, they started with a very grand idea and quickly realized that to make this work at scale and to enter the market in any meaningful way, they'd have to decide what to do and what to focus on. So while future Synthesizing plants may or may not have their solar collector field for thermal solar energy, I gotta show you this because what they did build here is freaking amazing. One of the problems with concentrated solar collection is that the hotter the cavity gets, the more energy radiates back out through the opening where that solar collection comes from. Conventional solar receivers hit a wall around 580 degrees, but that isn't hot enough for the chemical reactions needed for producing syngas. So then you shrink the opening to trap more heat, but then you can't get enough sunlight in. Their solution? flood the cavity with steam.
Here the concentrated radiation from the field enters, creates high temperature steam at 1200 degrees.
Sunlight passes right through, but when the hot walls re-radiate as infrared, the steam catches it, a one-way thermal trap. The greenhouse effect, inside a box, the same physics warming our planet, re-engineered to generate 1500 degree steam.
The steam exits above me here through this line. You see, well insulated, goes into the storage here, so charges the storage.
This is the one that surprised me most. Chemical plants need to run 24/7, and you can't shut down a Fischer-Tropsch reaction every night. So how do you store 1200 degree heat overnight?
This storage is 1 megawatt hour of storage.
Even in this size.
Exactly, yes.
Wow.
So the bricks is about 12 tons and the whole system is about 20 tons.
Ceramic bricks in an insulated vessel, storing 1 megawatt hour at 1200 degrees.
So you have inside, you have the bricks, which store the material, and then it's well insulated on the outside, such that you're not losing the heat to the outside.
The entire system is about 90% efficient, about a tenth the cost of battery storage, and there's no rare earth materials, there's no lithium involved at all. And then at the heart is this.
Here we have the reactor. So this is our gas-heated reactor.
7 tubes packed with catalyst. Then biogas, CO2, and water flow in at 10 bars while 1200 degree steam wraps around the outside, driving the reaction. No fuel burned to generate heat. Every carbon atom in the feedstock becomes product. And through this entire reaction in the reactor, out comes syngas, carbon monoxide, and hydrogen, the building blocks of fuel. Let's think about that for a minute. The most efficient reaction to convert solar energy into chemical bonds. 78% conversion efficiency at this scale and over 90% projected when this reaches full scale. All running on a reaction first discovered over 100 years ago on pure renewable heat. The syngas then flows through a Fischer-Tropsch unit built by their partner Ineritech, and out comes this.
This is the liquid fraction, so you see completely clean. And this can now be refined. You just take, this contains 60 to 70% kerosene, hydrocarbons, 20% diesel, and about 10% naphtha. So you need to distill, and then you get the fractions.
So just think about what that means. When fuel comes out of the ground, you get whatever else geology left in there. Sulfur, aromatics, heavy metals. When you engineer the fuel molecule by molecule, you design the output. In a lot of ways, this is a better alternative. And if we're going to make this work, it has to just work with the current infrastructure, and this does. The plant actually works and there's fuel coming out. Yes, this is cool engineering. We're talking about heliostats and 1200 degree superheated steam. But it's not just that. It's a lesson in how to solve hard problems in a way that might actually reach the market. Remember the snow on the heliostats? The plant runs intermittently. It produces thousands of liters, not millions. The solar receiver is a research tool here, not a production engine. I've been walking around thinking, this is freaking awesome, but how does any of this work outside of the Sahara or, Mojave Desert here in California? And that's when their engineering team stopped and told me this.
This whole thing is only a tower because of the solar receiver, which we have in the back. If this would not be operated, at least partially, with concentrated solar, then it would not be a tower. It wouldn't be a tower. We would build it on the ground.
I've been making these videos for almost 10 years now. And one of the most amazing parts is being on site with the team, because then you get to realize from them how they iterate and how they evolve their technologies or their process or where they invest their time, right? The tower, the mirrors, it's as amazing as all of that is, and it does work and it can be built. It's optional, but it doesn't have to be. You could just run a resistive heating element for the steam. And I told them about this. We made a video a couple months ago on a company called Atmos Zero, which is developing a 2-stage heat pump for industrial steam that could reach those temperatures. So instead of resistive heating that requires 100% of the electricity needed to produce that steam, a heat pump might be able to do it for about 20%, right? A quarter of the energy input. And their feedback was amazing. If that technology emerges, we could drop it in and use that instead. Because the heat source is not what their technology is about. It is cool, and a heliostat would be amazing, but ultimately they're a chemistry and reaction company. Germany's got a lot of solar, but it's not the ideal place for something like this. Depending on where you deploy these things, maybe it's solar heat in Morocco, wind electricity in the North Sea, curtailed nuclear in France because they actually have too much sometimes. Whatever the source of energy that you could use is, use it. We're entering chapter 2 now of the sustainable energy story, right? One where economics reign supreme. If you can't make this work because it's cheaper, it's going to be hard to roll this out, especially if the administration in charge has different priorities and funding dries up. Economics have to win out. And 2, you have to be hyper-focused on what you actually do best. It can't be too broad because this story, like I mentioned, is actually like 5 pieces. There's 5 different things to have done. And they've decided, let's just focus on this one part. Where you get your energy from, you pick. Even the Fischer-Tropsch process, they outsource it.
Our focus is syngas production, and the downstream processing is not our technology. However, what is our part is integrating Fischer-Tropsch into the overall process. So, for example, in Fischer-Tropsch, you also produce C1 to C4 gases like methane and so on, which can, here in this case, nicely be recycled back. So we just recycle, we loop it back, and we reform it again into syngas.
They buy commodity biogas. They partner with steel manufacturers for components. They have a narrow laser beam focus on the part that they actually do best. But even the best tech doesn't scale without a market demand. But what I didn't entirely understand before researching this video is that the market for syngas for aviation is being created by law. The European Union passed Refuel EU. Airplanes flying in and out of Europe have to use sustainable aviation fuel. 2% this year, 20% by 2035, and 70% by 2050, with a sub-mandate of 35% being synthetic e-fuels, not biofuels, synthetic. So this isn't like a good to have or bragging rights on your website. This is going to be law. And the gap is staggering. Airlines burned 300 million tons of jet fuel last year. Total SAF production, about 1 million. That's about 0.3%. The distance between what's mandated and current production might be one of the biggest market opportunities in energy.
Our target is really going below $1,000 per ton. So offering a true alternative for fossil fuels. And if you want to do that, you need to squeeze out everything in this chain.
Synthetic fuel costs 3 to 5 times more than fossil fuels today.
What are the biggest challenges to getting to that price?
It's scale, simple scale. You need to go to the locations which offer good feedstock, cheap feedstock, lots of agricultural waste. You need to have super cheap renewable energy, electricity, and then you need to have the capability of manufacturing plant components cheaply. And if you have those 3, then you can reach those low cost if you build plants at large scale. So it needs a scale of around 500,000 tons or something like that per plant.
Swiss Airlines has flown on their fuel. The next plant's entire output is sold before it's even been built. Every cost curve has to start somewhere. And they're not alone. Ineritech and HIF Global are racing too. But the scale-up plan is real. A commercial plant by 2027, 6 plants across Europe, a $1 billion project in Morocco at 100,000 tons per year. And for context, Europe burns around 38 million tons of jet fuel annually. So these numbers are still pretty much like a rounding error. But don't forget that so was solar in 2005. Everything does have to start somewhere. Remember when I said that the fuel has a benefit that it might matter even more than carbon? Well, here it is. Aviation's total climate impact is roughly 2 to 4 times worse than its CO2 alone. The reason is contrails.
When you form a contrail behind the airplane, which are ice contrails, which form because you have particles, soot particles in the exhaust stream.
Some researchers have even said that contrails are probably the largest warming effect caused by aviation, bigger than the bulk of CO2 combined.
And with those products, we quite significantly reduce the amount of particles. So we also reduce the non-CO2 effects of aviation.
So synthetic e-fuels, no soot, no aromatics, clean combustion, and fewer particles left and fewer contrails. So then, what do we know? The fuel does work. It's certified, and it's flown commercially already. It drops into existing engines in airports and planes without any changes to infrastructure or anything else. The chemistry and the reaction is 100 years old, tried and true. And the clean heat can come from whatever is available. The question was never, can we make jet fuel without oil? We know we can. We already do it. Like a lot of things that we do, The question is economics. Can we make it affordable enough? Otherwise, who would buy it? Why wouldn't you just buy traditional fuel and continue to profit from each plane ticket like we do now? Right now, the costs aren't close. The entire world's synthetic fuel wouldn't keep a single 777 flying for a year. The cost gap is just massive, and scaling up an operation like this is no small feat. But for the first time, the physics do work, and the regulations are locked in, and the money is flowing. I don't think synthetic fuels makes any sense for like passenger cars. Why wouldn't, EVs, and we'll have technologies for that. But how do you fly long haul routes? How do you fly from New York to London or San Francisco to Tokyo without something like this? It's hard to imagine. Nuclear powered planes, I guess that could work. This is an important topic. But what do you think? How important is sustainable aviation fuel? Sound off in the comments below. I'm Ricky with Vinci. Thanks so much for watching.